This is another test that can help us determine if a series converges or diverges, and it's called the integral test. Now this is why we did improper integrals before we did this section. It says if f is positive, continuous, and decreasing for x is greater than or equal to 1, then the series from 1 to infinity and the integral from 1 to infinity, where the sequence and the function there are the same thing or equal the same thing, then either both diverge or both converge. And there will be more tests coming up like this, where basically what we find is that two things do the same thing. So it doesn't. It tells us that they both behave the same way. So that means if we can find out that the integral converges, then we can conclude that the series converges. If we find out that the integral diverges, then we can conclude that the series diverges. One word of warning here: this does not help you find sums. Obviously you can find the sum of the integral, but that doesn't always line up with the sum of the series, and that's fine. They usually won't ask for it. They're just letting you know, even if you find a sum for the integral, it does not necessarily imply that is the sum for the series. It does tell you that they both converge, they just may or may not converge to the same thing. So just be mindful of that. So let's try this. It says we have the series from 1 to infinity of n over n squared plus 1. So what they're telling us is we can change this to an improper integral, and you can use x's or n's, whatever you want. And if you're not sure about improper integrals, you can always go back and check that video. But we get this, and then it's going to be a u sub problem. U will be x squared plus 1, du is 2x. Well, we have an x over here, but not a 2x, so we need to divide both sides by 2. And we will get the limit, as b approaches infinity, of 1/2 times the integral from 1 to b of du over u. And you should recognize that that is, in fact, natural log. So we have the limit, as b approaches infinity, of 1/2 times the natural log of the absolute value of u from 1 to b. So that's going to be 1/2 times the natural log of x squared plus 1. Just so you know, if you want to drop the absolute value signs, you can, because they are not going to be necessary when you have x squared plus 1, because it's always positive. So now we plug in the top. Minus, plug in the bottom. So we take the limit as b approaches infinity. Well, as b approaches infinity, natural log of b squared plus 1 also approaches infinity. So we don't really care that this is 1/2 natural log of 2. Infinity minus some little number is still going to be infinity. So this clearly diverges. And since the integral diverges, we can also conclude that the series diverges. Next example, we have the series from 1 to infinity of 1 over n squared plus 1. So we're allowed to change this into an improper integral, and I'm just going to skip to where we've already put the b in for the infinity. And if you look, the u sub won't work for this. This is actually arctangent. So this turns into arctangent. So we'll do the limit as b approaches infinity of arctangent of x from 1 to b. So we have the limit as b approaches infinity of arctangent of b minus arctangent of 1. And let's try this one in the calculator just so we get practice doing it that way as well. Go to y equals, plug in arctangent. Remember, that's the same as tangent to the negative 1 of x minus arctangent of 1. Now we want to see what happens as we go to infinity. So go to the table, plug in 10, 100, 1,000. See if I can... Doesn't seem to be letting me move any farther down. Oh well. You can see what's going on there. It's going toward 0.785, which turns out to be pi over 4. So the sum for the integral is pi over 4. Now that doesn't necessarily tell us the sum of the series, but the fact that the integral converges to pi over 4 confirms for us that the series also will converge. So again, don't get caught up in thinking that this number means anything for the series. It may or may not. but we can use it to determine whether the series converges or diverges. So the series does converge because the integral also converges. Alright, one more example. We have the integral of 1 over n natural log of n. Notice this one starts at 2. The reason for that is we can't do the natural log of 1 because that's 0, and 0 in the denominator is a bad thing. So we get the limit as b approaches infinity, integral from 2 to b of 1 over x natural log of x. Anytime you see natural log of x in an integral, it will be your u. Okay, if you notice, this actually works out perfectly. Let me rewrite this so it's really easy to see that. But 1 over x times 1 over natural log of x is the same thing. So we actually end up with the limit as b approaches infinity of, okay, u goes right here, and then this whole thing gets replaced with du, so we end up with du over u. So we get the limit as b approaches infinity of the natural log of u plus c. Oh, sorry, not plus c, but from 2 to b. So that's the limit as b approaches infinity, the natural log of the natural log. Hold on just a second. I got ahead of myself. Okay, this would be natural log of u right here, and then our u is the natural log of x. So that's what it should be. I apologize for that. Got a little ahead of myself. So du over u does become natural log of u, which is what I have right here. Then you plug in the u, you get natural log of x. Alright, I'll give you a little hint. Anytime natural log is being sent to infinity, it goes to infinity. So I knew as soon as I saw natural log right here that it was going to be a diverge. Apologize for my voice, dealing with a little cold. But let's go ahead and finish this out. Limit as b approaches infinity of the natural log of b minus the natural log of 2. So natural log of b does go to infinity, and infinity minus a number is still infinity. So the fact that the integral diverges tells us that the series also diverges. So the integral test allows you to use an improper integral to test the series. If the integral diverges, the series diverges. If the integral converges, the series converges. So the key here is the integral test tells us that they both do the exact same thing.